So, so in this last problem here, we have a tube section that has we're given its length, and we're given that it's subjected to an external torque of 200 newton meters. We're given the material properties of the material, and we're asked to find the shear stress distribution on the wall, on the wall, on each wall thickness. Okay. So what we have to do now is if we look at each of our cells here, each of these have different walls. So I'm going to quickly calculate the shear stresses real quick. So we have Q1, Q2, Q3. Okay. So wall 1 I'll define as this being this section here. Okay. Wall 2 I'll define as being this section here. Wall 3 I'll define as being this section here. Wall 4 I'll define as being this section here. I'll define this wall here as wall 5. And then this whole outer section here will be wall 6. Okay. So for each of these, we can determine what is our shear stress. So our shear stress would be equal to the net shear flow divided by the thickness of the wall. So for T1, that would be equal to, there's only Q1, is the only shear flow it's experiencing, and that would be divided by T1. Okay? All right. T2 or tau 2 would be equal to Q2 divided by the thickness T1 of that wall. Q3 would be, tau 3 would be equal to Q1 minus Q2 over over the thickness of that section, which is again T1. The shear stress in wall 4 would be equal to Q1 minus Q3 over T2. Okay, and then tau 5 would be equal to Q2 minus Q3 over T2. And then tau 6 would be equal to just Q3 over T3. Okay. All right. So are there any questions about how you can? So we don't know what Q is yet in each of them, but is anyone confused on how you can define the shear stress within each of the individual walls? Okay. All right. So we're good there. All right. So so in order to determine what our different shear stresses are, shear flows are, we need to use our equations that we developed for multi-wall tubes. Okay? So we need to have our equation for T and our equations for the angle of twist for each of the cells. Okay? So in this case, we have 3 cells, so we're going to have 4 equations that we're going to have. So the number of cells plus 1 is the number of equations you have. So we have 3 cells, we'll have 4 equations. So the first equation is just for the overall torque. So the overall torque is going to be equal to 2 times the sum of the shear flows in each of the cells times the area of each of the individual cells. Okay, so if we do that, we have 3 cells, cell 1, cell 2, and cell 3. So for cell 1, the area of cell 1 would be equal to 1/4 of a circle, so it'd be equal to 1/4 times be equal to 1/4 pi times the radius squared. In this case, the radius is equal to a which is just a constant here, right? And then the flow in that cell is just equal to Q1. For cell 2, it's a rectangle. That's area would just be equal to A times C minus A. Right? So this is for cell 2, and then the flow would be equal to Q2. And then the last one would be for cell 3. And cell 3 would be equal to just B times C would be the area times Q3. Okay. So that's our first equation. All right. Then we're gonna have three equations, one for each cell for theta. Okay. So for cell 1, theta is going to be equal to 1 plus VL over E A1 integrate of Q ds T of S. All of these terms out in front here are constants, so they'll just remain. So the only thing that we have to do most of the time is we have to evaluate this integral here. Okay? So if you evaluate this integral here, what we end up getting is for the first cell, the wall that's on the top right here, or top left, right? That wall, right? The length of that wall is going to be equal to 2 pi times the radius A. Okay, so that's the perimeter of a circle divided by 4, since it's a curved section. Since it's only a quarter of a circle. All right, so that's our S. All right, the shear flow over that part of the cell is just equal to Q1, and then the thickness over that part of the cell is equal to T1. All right. So that's for the first part of the cell. The second part of the cell, which is wall 3, which we defined earlier, is going to be equal to is going to be equal to shear flow over that section is going to be equal to Q1 minus Q2 over the thickness of that section, which is T1, times the length of that section, which is just A. Yeah. Okay, and then the last part of the cell is shear flow is equal to Q1 minus Q3 over T1, I think. Is it T1 or T2? It's T2, sorry. Times times A again. Okay? So that gives us our first equation here. The only terms that are unknown in this equation are our Q terms. Everything else is a known value. Okay? All right. And I'm sorry, and theta is unknown. All right. So we can repeat this process for the next couple of cells. I'm not going to explain each of the individual cells because it's going to take a lot of time to do that. Okay, so let's just go through it. And if you have a question about what I'm doing, please just stop me as I'm going along. All right. So for the first wall, which is wall 2 that we defined earlier, it's going to be the shear flow on that wall is equal to Q2 over T1, and then the length of that wall is going to be equal to C minus A. Yeah. All right. Then for the second part of the wall is going to be equal to, I'm sorry. Sorry, there's actually two parts of it. Is C minus A plus A for the top of the section and the right-hand side of the cell. So the top of the section here and the right-hand side of the section here. The second part of the cell is between cells 2 and cells 3. So the shear flow would be equal to Q2 minus Q3 over T2. And then the length of that would be equal to C minus A. All right. And then the last part of this, with this term here, would be equal to the wall between cell 1 and cell 2. So that would be equal to Q3 minus Q1 over T1. Or sorry, it should be Q2, not Q3, Q2. Q2 minus Q1 over T1 times the length, which is in this case is just A. Are there any questions about any of the terms here in that integral? All right, cool. All right, and the last one would be for cell 3. So for cell 3, we would get theta would equal to 1 plus V L over E A3, integrate from 0 to S, Q of T of S ds. So the 1 plus Poisson's ratio L E over A3 is a constant still. So the only thing we have to do is evaluate the last integral here, right? So the last integral, if we look at the outside of our section here, all right, there's only the shear flow over that section is constant. It's equal to Q3. The thickness over that agent is also constant. It's equal to T3. All right, and then the length of that section is equal to B plus C plus B. Okay. All right, the next section is between cell 3 and cell 1, and the shear flow would be equal to Q3 minus Q1 over the thickness of that wall, which is equal to T2, and the length of that is just equal to A. Then the last part of the equation is going to be equal to between cell 3 and cell 2, so it's going to be equal to Q3 minus Q2 over T2 divided by, times the length of C minus the length A. All right. So what we end up having here is we have four equations with four unknowns. Our four unknowns are theta, Q1, Q2, and Q3. All right. So to solve for these four unknowns, by far the easiest method is to then rewrite these four equations in a matrix. Okay? So we're going to rewrite these four in a matrix. Oh, my computer died. All right. So what we'd end up getting is we would have a 4x4 matrix with, these are all known coefficients of these terms. Okay. And then you'd have a set of constants that are known. So if you rearrange these four equations here into here, all you have to do is take the inverse of this matrix, multiply it by your known constants, and you would get your unknowns. Okay? So if you did that, what you would end up getting is you would get theta would be equal to 0.193. Q1 would be equal to 24.62 kilonewton meters. Q2 would be equal to 25.11 kilonewton meters, and Q3 would be equal to 38.6 kilonewton meters. Okay. All right. Now, in order to calculate, so once we have theta, once we have the shear flows, it's really, well, the only thing we really, theta is good, but we really need is the shear flows. So using these three shear flows, we can calculate our shear stresses in each of the walls of the system. Austin and Michi, are you following that?
Kind of.
Yeah.
Okay, so you have Q and tau and T. Like the only thing you didn't know in these shear equations for each of the walls of the cell was the shear flows. The Q
Right. So
number,
now
right?
we're just using those Q's that we just solved for to find the shears.
Exactly. So all you're doing is just plugging those in, okay? And you know the thicknesses they were given to you in the start of the problem. Right?
Right. That makes sense.
Okay? So then all you're going to do is just plug them all in. So if you plug them all in, so if you plug in tau 1 is equal to 8.21 megapascals. Tau 2 is equal to 8.37 megapascals. Tau 3 is equal to 0.163 megapascals. Tau 4 is equal to 6.99 megapascals. Tau 5 is equal to 6.75 megapascals, and tau 6 is equal to 7.72 times megapascals. Okay. Right. So that would be your answer there. Okay. So Manji
And then
and Austin, you're the only ones here, so feel free. Like I'll be here. It is office hours, so if you have any questions, I'll be happy to help you here. So
okay.
Go ahead.
And for the tau total, it would just be the sum of the Q over the sum of the thickness.
So are you talking about this top equation here?
That, yeah, Q net over T.
Yeah, so that was just the definition of the shear stress
Okay.
within each wall. So I was just using that to explain how I got the different numbers for each of the walls. You don't have that's not an equation you need to solve. You only
Okay.
care about the stresses within each of the walls.
Understood. Okay. Thank you.
Yeah, no problem.
All right. Well, thanks for finishing that problem for us.
Yeah, no problem.